Well, hello everybody. Welcome to another episode of Master the NEC, where we talk about the National Electrical Code. In this video series, we're up to the part for transformers where we talk about grounding and bonding. Now, we're going to talk about how to size the supply side bonding jumper, the system bonding jumper, grounding electrode conductors. We're going to be very brief with that because we have a whole other series on grounding electrodes and grounding electrical conductors and whatnot. We're going to talk about the equipment grounding conductors that are bought to the primary side of that transformer. But remember, we're going to go over the basics, okay? We're not going to be able to cover every aspect that you'll run into, okay? So we're going to keep this very focused on a single transformer. Now remember, I could have a single transformer that supplies multiple panels. So I could have multiple sets of secondary conductors. And so sizing a system bonding jumper might be differently, whereas instead of sizing it for a single enclosure, I might be sizing it for multiple enclosures, or I could have one single system bonding jumper that has to take into account all of the sets that are running to those other panels. Okay, so it gets kind of complicated, but we're going to try to keep it as simple as we can to a single transformer because I really need to teach the basics. If I were to go into all the possibilities of Article 450 and 250.30 and all those aspects for transformers, then we'd probably turn into an extensive, longer series than what it is. So we really want to talk about the basics. Now, before I get started into that, I had a question that came, and again, we've done other series up to this point. So you should have watched Series 1 where we talk about how to size the primary current on a transformer and the maximum secondary current on a transformer using the formula. You already should have in part 2, you learned how to size the overcurrent protective device for the transformer's primary and for the secondary. Where applicable. And we learned all those things, and then we went on and learned everything about the tap rules in part 3, and then we did secondary conductors in part 4, and we moved on up. And so now we're talking grounding and bonding. But what I wanted to go back for a second and talk about table 450.3b, because there's a top portion of that table that I chose to not go in real in depth into, but I figured I'd better go on and explain it since I've got you in this series and you've got to this point and you probably have gone, well, when do I not need a secondary protection of a transformer? Okay, well, typically it's not going to be an issue because you're going to usually go into a panel board, and the panel board is required to have protection in the panel board in 408.36. Those secondary conductors are going to be sized based on terminating into those overcurrent devices, based on the secondary conductor rules and whatnot. But for practical purposes, let's talk about when I don't need a secondary protection of a transformer. Okay. Now, I still have to protect those secondary conductors, and I have to install them in accordance with the secondary conductor rules. And if they terminate in an overcurrent device, they have to be rated at least equal to the equipment or the overcurrent device that they terminate into. That didn't change. That's all the same. But let's talk about the table. So let's go on and look at the code. And I'll go on and go to the NEC. And let's go on and go to that area of the NEC real quick, the 450.3, because I want to make sure I cover that in case somebody says, well, what does that table mean? Because there's always something that we leave out that I want to be able to cover. So here's the table. Now what we're talking about is this portion up here. This right here. This. When somebody sees this, they think, well, when can I have primary only protection and not require secondary protection? This is, again, of the transformer. That's what we're talking about. Well, as long as that primary overcurrent protection device doesn't exceed 125%, and yes, note 1 does apply, which is if it doesn't correspond, you go up to the next non-adjustable circuit breaker or fuse rating. If that's the case, then I don't need any secondary protection for that transformer. Okay? Now, that is very true. Just remember that that has nothing to do with protecting the secondary conductors. That has nothing to do with the fact of those secondary rules in 240.21c, 2, 3, and 4, whatever, that actually terminate onto an overcurrent device inside of a panel board. The panel board that we are familiar with in our graphics, for example, has to be protected, has to protect that panel board. So it has to have an overcurrent device in accordance with 408.36. Okay, so it's generally going to be there. Now, incidentally, those conductors that are coming from the secondary, using the secondary conductor rule, can go 10 foot or 25 foot, depending on the rules that apply. They're allowed to go and not have overcurrent protection at the transformer due to these rules. Okay, but they do terminate in an overcurrent protective device, and that is in the panel board. So in a sense, you do have secondary protection here, but it's not really for the actual transformer secondary protection if you've got 125% as your maximum on the primary side. Okay, it's not required. Now, again, when we say it's not required, it says that in the table, not required. Typically, it becomes not much of an issue because we are going to size a transformer protection, overcurrent protection on the primary side. Usually we could go up to 250%, and we saw why we might do that in other episodes of this video series. But typically we go to 125. So in theory, since we only went to 125, we wouldn't need secondary protection on that transformer. However, since we're going to terminate in a panel board, then we are going to have some type of protection on that secondary. Okay? Now, if we do have primary and secondary protection, then the primary can't exceed 250%, and the secondary can't exceed 125%. And we kind of covered that already. But I just wanted to give you that example where you did not necessarily need secondary protection on the transformer if the primary protection doesn't exceed 125%. Okay? Where might I run into that in some cases? Well, you might have an application where I have 125% maximum primary protection. The secondary, you have the transformer, it comes out and it hits a disconnect. And that disconnect, and then there's no panel board in it, it's just a disconnect. And then it feeds downstream a panel board, which would be acceptable under 408.36 anyway. It's still considered protected. All right, if that's the case, then that has primary, secondary protection, and you would do no more than 250 primary, and the maximum is 125 secondary. Okay, but if you're coming off like our graphics and hitting a panel which has the actual main breaker, let's say, just call it a main breaker for that panel board, then that's protecting the panel board, and that's what it's there for. Now, those conductors that are on the secondary are going to have to be sized to handle whatever the rating is of that secondary, of whatever the rating is of that panel board's overcurrent protection anyway. Okay, so you really becomes a moot point. But if people wanted to know, yes, you can have a secondary of a transformer not protected, because directly it is protected from the primary as long as you don't exceed 125%. Okay, so that's kind of what that rule was. For most of us, we're not going to worry about it too much because this is what we're going to look at. This is what we normally will see. Okay, so we have our primary protection, we have our secondary protection. Although it is here to protect this panel board, these conductors are sized based on this. This is a 10-foot secondary rule. Then if this is a 300 amp rated device, then these conductors will be rated for 300 amps. Even if we know that the secondary of this transformer is not going to put out enough current to be able to handle whatever the load would be. So if this is 300 amps, remember if we were back in our part 1 series, that in order to calculate the secondary current, it was 75,000 divided by 360, which is 208 amperes. Okay, so it can only put out 208 amperes. Okay, but the secondary protection could go up to 125%. But if this primary was limited to 125, then technically we wouldn't need any secondary protection here. But for all intents and purposes, we don't worry too much about the top one because usually this is going to be your configuration right here. Okay, just know that if you didn't have a panel board here on the secondary and you were feeding something, then you would not necessarily need secondary protection. Okay, unless your secondary conductor rules stated that you did. Okay, all right, so let's get back to what we're dealing with. All right, so primary side, we sized this at 125% if you watched our previous videos. So this was, it was 90 amperes is what we calculated out as the primary current rating. At 125%, that was 115. It didn't correspond, so we put it on a 125. That's the next largest size, okay? We were able to do that. These conductors here that we're running down are rated 2 gauge because they're good for 115 amps at 2 gauge, but we're terminating on a 125 amp breaker, so we want to make sure they're protected at their ampacity. So we wanted this to do double duty. So we're actually at a 125, so that's going to serve to protect the transformer as well as protect the conductors. Okay, and if you didn't understand any of that, you need to go back and watch episode 2 of the video to understand of this series to understand why we did that. Okay. Now over here, we calculated previously at 208 is what our secondary, and we did it 125%. That was 260. Didn't correspond to a breaker, so we were able to go up to 300. So if this was a 300, these conductors have to be rated for 300 because we can't use a next size up rule on secondary conductors. So these are rated at 300 amps. So when we go to 310-15B16, we'll see that these need to be 350 kc mil, which is good for 310 amps because 300 was only good for like, I don't remember exactly what it was good for, but it wasn't good for 300 amps. Since this was 300 amps, it had to terminate in 300. It's like 285 or something like that. Okay, and you can't use the next size up rule because it says you can't in 240.21c. All right, so that's what they are. Now, remembering, let me bring it back and just talk about something. I could have a transformer that is only putting out 208 amperes, okay? And of that 208 amperes, could it terminate? Could you have a 200 amp panel as a secondary? Absolutely. You don't need to use all the 208. But you have to calculate your load so that it's not going to exceed what the transformer's rating is. And a lot of people do that, and they'll overload a transformer and will burn it up. Okay, so if I wanted to have a 75 kVA transformer with a 208 secondary current, and I wanted to put a 200 amp panel on it on the secondary side, then that's fine. And the conductors that are feeding it would be based on the need to have conductors that would be good for 200 amperes. And they would terminate into a 200 amp main breaker of the panel. And that main breaker protects the panel in accordance with 408.36. And if that's the case, then I'm fine. I'm okay. I didn't need that extra 8 amps, if you will. Okay? I like getting all my amps for my money, but it doesn't matter. Could I have a transformer that's sized much, much larger, like a 500 kVA transformer, but I still only have, let's say, a 200 amp panel or whatever? Now, that's perfectly fine too. Again, the transformer can always be larger. What you want to be careful is that you don't have a transformer that's too small. Now, hopefully you don't size your transformer until actually you've balanced your loads, as well as selected your panel size, and let all of that dictate the transformer. And engineers will move that way. You don't start with the transformer and then size your panels. You look at your load, you balance out your loads, and we're going to do a video. Next video is going to be on balancing transformers for Y and delta, and how to balance panels, and how to then size your transformer based on that information. But what we're trying to say is, could I have a transformer that has multiple panels supplying it and that transformer be oversized? Absolutely. We just want to make sure that we don't have a transformer that's undersized. Okay? All right. That's just the key point I wanted to say there. All right. So in our case here, go back to the graphic. If we go back to the graphic, then this one here, just in our case, this was only 208 amp output, but using the 125%, we ended up sizing this at 300 amperes. Now, in the real world, it's probably not going to work, because if we were to say that this is really not the protection for the secondary, because this was not higher than 125%, then I would really only size this based on my calculated load. So even this is 208, then I have to know my calculated load. Even though this might be a 300 amp device and these conductors are rated for 300 amperes, my load itself, it cannot exceed whatever the maximum output of this transformer is. Otherwise, I'm going to cause problems with this transformer. So I might have only 190 amps of load on a 300 amp breaker. Well, because you could have different loads in here. And these conductors are good for 300 amps, but it would be pointless because this transformer can only put out 208. So that's why it's important to understand that possibly I can use the 125 here, and this right here could be simply based on the load necessary. Remember, it can go up to 125% even if it was secondary protection, but it doesn't have to be, okay? But it at least has to be 208 amps, because we know that this transformer could potentially put out 208 amps. So typically what I would probably do, we're not going to do that in our example, but what I would probably do on this transformer to be efficient is I would probably do this at a 225. And I would size these conductors for 225 amps. And I would make sure my load doesn't exceed 208, but my breaker would be at 225, and that would be perfectly fine as long as I calculated my load. Okay? Remember, folks, I could have a 1,000 amp overcurrent device as long as my load doesn't exceed it. So if I've only got a 500 amps, what's the problem? I have many times where I have a 200 amp panel, but my load's only 180 amps. It gets done every day, right? So same thing would apply here. So in our case, in real all practical, if this was a 75, I probably would put a 225 here. Size these conductors for 225. Make sure my load is actually less than whatever the transformer would be with 208. And then make sure I balanced all my loads in here so that I'm not overloading any of the windings on this transformer. So everything's good. We'll talk about balancing in the next video. But in our video, we are going to say we did this at 125% of whatever the output was here. In that case, so this was 260. It didn't correspond, so we made this 300, and this right here is 350 kc mil. Just go with that, because that's what we're going to use to do our grounding and bonding. Okay, I just want to lay the lay of the land. Okay, all right. So now let's size this equipment grounding conductor. Well, we know this is a 125. We know that we use 250.122 to size equipment grounding conductors that are on the load side of the overcurrent protected device. So based on that, we're going to go to the National Electrical Code. And we're going to go to 250.122. Size that little sucker. All right, let's go here and here. Okay, so 250.122, based on the overcurrent device ahead of it, we said it was 125. It falls between 100 and 200, so we're going to use the 200, because obviously it's not less than 100, so we can't, or less, so we can't use that. So we're going to be a 6. So it's going to be a 6. All right, so in this application here, this equipment grounding conductor is going to be a 6. So we got 2-gauge conductors and we got a 6-gauge equipment grounding conductor. So we're done there. Now let's do this supply side bonding jumper. Now we're going to size this supply side bonding jumper, okay, in accordance with 220.30A2, which ultimately is going to tell us to go to 250.102C, but it's going to be based on these conductors, these right here. And these are called the derived conductors because they're derived from the secondary of this transformer, okay? If you think of derived as another word for newly born, okay? So, newly borns, right here, we're going to size those. So let's go look at what the code says first in 250.30. Now remember, 250.30 is going to be an important place to remember because that's where you're going to get all the rules that have to do with the system bonding jumper sizing, grounding electrode conductor sizing for separately derived systems, all those goodies. Now they're going to send you other places in the code, but that's where you want to go to have your foundation, if you will. All right, so here we are at 250.30. Simply, and remember, so 250.30 is important because that's where you're going to get all your grounding and all the aspects of separately derived systems. All right, so when we got to do the system bonding jumper, we'll look right here. But right now, we're doing the supply side bonding jumper right here. All right, now remember our graphic. We have a transformer and we have a separate panel that has the first disconnection means in it. Okay, so if the source of the separately derived system and the first disconnection means are located in separate enclosures, in our case they are, it says a system bonding jumper shall be installed with the circuit conductors, okay, from the source enclosure to the first disconnection means, all right, and we did that. It says a supply side bonding jumper shall not be required to be larger than the derived ungrounded conductors, okay, in our case the derived ones were 350 kc mil, so they doesn't have to be larger than that. I can promise you it won't be. It says the supply side bonding jumper shall be permitted to be non-flexible metal raceway type or of the wire or bus bar type, or the bus type as follow. Well, in our case, we used a wire because the EMT also went to FMC, and so the FMC is not a non-flexible metal raceway. It is a flexible metal raceway, obviously by the name. It's a flexible metal conduit, if you will. So if it was all EMT, then I can get away with not having to put a supply side jumper in it. But it's not, so I do. So we're going to use the wire type. So in the wire type, it says the supply side jumper of the wire type shall comply with 250.102C, and that's how we get this to that area of the code. And it is going to be based on the size of the derived ungrounded conductors. Again, in our case, black, red, blue, they're the derived ungrounded conductors in our system. All right. Now, incidentally, what is the bus bar type? Just to let you know, there are systems where you actually have a bus bar that connects between enclosures, and in that system you can utilize the bus bar. And usually in those systems that are designed that way, usually there's separate enclosures that are still ganged, and you might have a higher voltage source, a transformer, a separately derived system, and you might have the enclosure right next to it, and it's a mutual bus bar that interconnects it, and that would be what you would use, and that would be fine, okay, in that type of system. What I tend to use doesn't. I use the wire type for my design because it's easier to be able to explain sizing and how we look at the graphic. Okay. So let's go back to the code. All right. So we're going to size it based on 250.102C. So we're going to jump around a little bit. Okay. But all right, to do that. So let's just do this here. And I'm going to go to 250.102C. Actually, I'll just jump down to it because it won't take but a second. There we go. Right there. All right, so it says based on C. Now, C says supply side bonding jumpers. Now, our case, we have only one single raceway. That's all we've got. One single raceway made up of EMT and FMC. It says the supply side bonding jumper shall not be smaller than specified in table. So we're going to go to the table 250.102C1. That's what we're going to deal with. So here's the table right here, right there. Now this table does grounded conductor minimum sizing, main bonding jumper, system bonding jumper, supply side bonding jumper, all of that's all good right here. And of course we are going to use it for our system bonding jumper sizing, and are going to use it for our supply side jumper sizing, okay? And in the next video, we'll talk about the grounded conductor sizing and some of the rules, and I'll show you the formula to size them based on the unbalanced load and all that. But right now, just this is what this table is all about. All right, in our case, the derived conductors were 350. Now remember here, it says over 3/0 through 350 and then over 350 through 600. I've seen many people in the exam accidentally go here and choose the 1/0. Now, in the reality of the real world, it's not going to be a problem because 1/0 is larger than 2, and that's okay. It's not a code issue. But on an exam, you want the best possible choice. So the best possible choice is right here. It's 3/0 through 350. Okay, so it includes 350, and that means it would be a 2 gauge. Okay, so when we go back to the presentation, this conductor right here, supply side bonding jumper, is going to be size 2 gauge. Now remember, these were 350s, is the derived conductors, and this right here is a 2 gauge. So there you go. So that's your supply side bonding jumper requirement. All right, now let's go on and supply the system bonding jumper. Let's see how we size that, okay? And the system bonding jumper, because it's a wire type, is allowed to connect the connection for the equipment grounded conductors as well as the grounding electrical conductor over to the XO. That's under the exceptions that allow it to do that. So otherwise, you could have one big terminal bus that has the XO and a bunch of lugs, and all of these grounded connections could all be made to the XO. Okay, it wouldn't be a problem either. But in this case, we're utilizing the allowance under the exception to use a wire type system bonding jumper, and then I can use that to connect this equipment grounding bus lug over to the XO. And it means that I can take GEC to this location rather than everything having to go to here. Okay? Okay. So we did that. So let's do this SBJ. So let's go back to the code, and we're again going to go back to our familiar area in the code we said to remember, and that's 250.30. We're getting all our guidance from there. So when we go back to 250.30 here, now we're going to go to 250.30A1. It says how to size that that system bonding jumper, SBJ. Okay. It says the unspliced system bonding jumper shall comply with 250.28A through D. Okay. All right. A through D. It also says that this system bonding jumper, the connection shall be made at any single point in the separate drive system from the source actually to the first system's disconnection means. Okay, so it could be in the transformer or it could be in the first disconnection means. Typically not to be installed in both. It can if there's not a conductivity between them. And then it's possible that it could be in both, and that's under the exception number 2 if there's no parallel path for grounded conductor. But in reality, most people choose either one of the or. Most people are going to put them in the transformer rather than in the first disconnection means. Okay, but anyway, there you go. That's the rule. Now, sizing is over here, 250.28, and the material. Okay, for our system bonding jumper, in our case, it can be copper or other corrosion resistant material. That's copper, or it could even be aluminum, because aluminum is corrosion resistant, okay, despite what people might think. The system bonding jumper can be wire, bus, screw, or similar suitable conductor. Now, similar suitable might be something that's provided by the manufacturer. If you want to do your system bonding jumper inside of the panel where the disconnect would be, then you might use the screw. That sometimes we call that the main bonding jumper, but it could be the system bonding jumper if you're doing all this inside of the first disconnection location. All right, that's possible. Just remember that your grounding electrode conductors also got to go to the same place wherever you do this system bonding jumper location. Okay, just keep that in mind. In our case, we use the wire. All right, again, if it says it's a screw, it's got to be green finish, visible after it's installed and what that, if you want to use that option. We're not, we're using the wire. Now get into sizing. 250.8 just gives you all the methods to make the types of connections. So pressure connections, all those type of things are all listed under 250.8. That's the different types of permitted terminations. Sizing now. System bonding jumper sizing. It's going to be sized in accordance with 250-28 D1 through D3. All right, well, D1 is basically the one we're going to deal with because we only have one enclosure that we're supplying from this transformer application. So it says main bonding jumpers, in our case, system bonding jumpers, shall not be smaller than specified in table 250-102C1. Well, we've already done that, okay? And we know that it can't be smaller than that. It's all based on the size of the derived conductors, okay? We know that, okay? So we're going to go back and look at the diagram. And so here, since this was a 2, then same application because it's still 350 and it's using the same table, so we can deduct that this is actually going to be a 2 as well. So this would be a 2. So the system bonding jumper would be a 2 gauge. The supply side bonding jumper would be a 2 gauge because, again, it's all based on these derived conductors. Okay, so we've done all that sizing. Now, what about this grounding electrode conductor? Well, if it's going to a ground rod, it would be just 6 gauge copper or 4 aluminum. Of course, you got to be careful not to terminate 18 inches of the earth. Okay, but you know, it could be aluminum. But generally, you know, grounding electrode conductor, if it's concrete encased electrode, it'd be no larger than a 4. If it's a ground ring, it doesn't have to be larger than a 2. If it's a water pipe ground or in-ground steel, then you're going to have to use the table 250.66. Now, 250.66A is for ground rods and plates and pipes that are used. 250.66B talks about the use of a concrete encased electrode, allowances, and of course, and we might as well go look at those because you know what? When I'm telling you about them and you don't see them, you might be thinking, well, I don't know what he's talking about. So let's go on and go there to 250.66 and you'll see what I'm talking about. Okay, so the general rule tells us to use the table. However, it says except as permitted, so it's a permissive rule. If your electrodes are rod, pipe, or plate, then the conductor, grounding electrode conductor, doesn't have to be larger than a 6 copper or 4 aluminum. Okay. If it's a concrete case electrode, then it doesn't have to be larger than a 4. Notice it doesn't give aluminum allowance there. And then it says here for ground rings, it says if the grounding electrode conductor or bonding jumper connected to the ground ring, as described in 250.52A4, does not extend onto other types that are larger, then the ground electrode conductor shall not be required to be larger than the conductor used for the ground ring, and that is a 2. Okay. If that ground ring happened to be larger for some reason, made larger than 2, maybe the engineer designed that, then it doesn't have to be larger than the conductor used. So even if you do utilize the ground ring, you got to go with whatever the engineer specifies for it. But generally, it's a 2 gauge is what's required is for the ground rings. Okay. All right. So that's that. But let's say it was a water pipe ground or in-ground steel. Then you would use the table. And that's the case. And you go down here to the table. Now, this is, again, going to be based on those derived conductors. Okay. And in our case here, it was 3/0 through 350, so it would be a 2. And that's what you would run to that electrode if it wasn't one of the ones that allow for smaller ones. Okay? Notice this table looks very similar to 250-102C because 250-102C was derived from this table. The only difference really in the two tables is that once you get sizes of over 1100 kc mil, copper or 1750 aluminum, when it comes to grounding conductor, bonding conductors, system bonding jumper or supply side bonding jumpers, then you would have to use a 12.5% rule, and it can't be larger than that if your conductors happen to be larger than that, or even parallel equivalents were larger than that. Then you run into that aspect. But when it comes to the grounding electrode conductors, they don't have to, at no time do they have to be any larger than a 3/0. That's the maximum size, and it would be 250 for aluminum. It's the maximum size that your grounding electrode conductor would have to be. Never has to be larger than that. Okay. All right, so let's go back to the graphic. So what we've done at this point is we've sized the EGC. We sized the supply side bonding jumper. So over here it was 6. Over here it was a 2. The system bonding jumper was a 2. The grounding electrode conductor, in our case, let's say it's ground rods, so it would only be a 6. And so we've done it. So now let's deal with the bonding here and here. Okay, so this FMC is not being used as an equipment grounding conductor. One, because the circuit of the conductors that are protecting the conductors in it are larger than 20 amperes, and the fact that this FMC in our case is larger than 1.25 inches. So all those things mean you couldn't use this as an equipment grounding conductor. Well, that's the reason why we put a wire type equipment grounding conductor in it. Now, if this was EMT all the way to here, then that would qualify as an equipment grounding conductor, and I wouldn't have had to put the wire type in there. Okay, and it would have been already done. Now over here, same thing. This is FMC. It's not being used as an equipment grounding conductor. For one, it's larger than 1.25 inches, but secondly, we know for a fact that these conductors that are in it are terminated on devices that are larger than 20 amps. So it is permitted to be an equipment grounding conductor under 250.118 where it is 20 amps or less protecting the conductors that are inside of it. Well, that's not our case here. So don't have to do anything with that part of it. Now, it is metal, okay? And this is where I see a lot of misconceptions online. It is metal, so it does have to be bonded. However, here's where some confusion come in. A lot of times people will loop things through it. They'll loop their supply side bonding jumper through it, or loop their equipment grounding conductor through a bonding bushing and all those kind of things. And so I want to discuss that a little bit because there seems to be a lot of misconfusion with that, and we're gonna dispel that right now. Okay, let's come back to me because this could get deep. All right, I'm looking kind of green, so I guess I didn't correct the tint on this video. Sorry about that. Maybe I'm just feeling green by all this grounding and bonding talk. All right, so on the supply side or the line side of this transformer or the primary side of this transformer, these conductors are 480 volts to ground. Okay, so there's a little thing in the code. Let's look at it backwards. Since they are first things first. You're never going to have punched holes in transformers. The sides are just too thick. You're going to have to cut your hole. All right. So when you punch that hole, we're going to hope that you punch it the right size. Okay. Transformers have specific areas near the bottom that they want you to punch, that you punch through. And so you would cut into the side of these things. All right. Now we will talk about what ifs if they were concentric or eccentric, but for the most part, you wouldn't have to worry about that because they're going to be punched holes. Now, if you punch the hole incorrectly and got a reducing washer or something, then that's a different story. That's an impaired knockout or an impaired portion of the connection. So then you got to do something else, and we'll look at that. But normally, you're going to punch it. It's going to be the right size you need. You're going to know what you need before you do it. Okay? All right. In 250.97, it says that for bonding aspects, when you're dealing with over 250 volts. Now, of course, on that primary side, we are over 250 volts. We're 480. Now, I hear a lot of people on the internet say that you don't have to do anything to that FMC at all because it's not an equipment grounding conductor. And you're absolutely right when it comes to that. But it's still got to be bonded, okay, in the general guiding rules of 250 because it could get energized. However, it can get where it's not as complicated as you think it is, okay? So let's look at it. All right, so we're going to go to 250.97. We're going to work on the primary side first, okay? So let's go to the code. And I'm going to go to the primary side. And let's going to go to, all right, hold on here. Actually, you know what? I'll just go backwards to it. It's a lot easier. Oh, actually forward. 250.97. There we go. Okay, right here. All right, so bonding for over 250 volts. All right, let's read it. Real important. It says for circuits of over 250 volts to ground, and of course a 277 480 would be, a 480 would be, all that goodies. A 208 120 would not, so don't worry about that. It says the electrical continuity of metal raceways, which that FMC is, and cables with metallic sheathing, that's be like an MC, that contain any conductor other than service conductors, and obviously these aren't service conductors we're talking about, shall be insured by one or more of the following methods specified for services in 250.92b. Okay, let's come back to me. B is all of those rules that what we're going to do for service conductors. It's kind of called assured because there's no overcurrent protection ahead of it. There's just kind of maybe an overload protection there, but it's really no overcurrent protection that are taking place when you're dealing with services. So we had these really more stringent applications of bonding. So with the transformer, you really do have some protection ahead. But in this case, we're still dealing with a circuit that is over 250 volts. So we got to find these rules. And so these rules are saying, hey, by the way, treat it like service conductors. But we do have an exception. And that's usually becoming the rule now. But we have the exception. But let's assume we don't use the exception yet. And we have perfectly punched out openings. Perfectly punched out openings. Let's go over to 250.92b and see what our options are. Okay, we're not looking at the exception yet. All right. Another thing to remember is that we can't use exception B1. Okay, and that is where we're making a connection to the grounded conductor in order to make that bond. And we can't do that, but we got 2, 3, and 4 that we could use over there. So let's go back to it. So I'm going to go to it, and I don't have to go very far. It's right here. Okay, methods of bonding at the service. Of course, we're not dealing with the service, but we're utilizing it like we're doing at the service. Okay, so what it says here is, okay, well, if you have bonding jumpers are going to be required if you got to go over unimpaired connections, reduced washers, oversized, if you screwed up, if you will, concentric or eccentric knockouts, then you're going to need a bonding jumper. And it also reminds us in that case, you're not going to be able to use a standard lock nut or bushing. Now, you can use it for mechanical. That means holding the raceway in place, but you're not going you can't use a standard lock nut for this application. All right, now what are our options? Well, remember, I can't use 1 to do that bonding, okay? But I can use 2, 3, and 4. So again, we're not using any exceptions in 250.97. We're just using these, okay? It says connections utilizing threaded couplings or threaded hubs on enclosures if made up wrench tight. Well, that's not really an issue in ours because we're not talking about hubs or Myers hubs, or we're never talking that. So that really is not going to come into play for us. The next would be threadless couplings and connectors if made up tight for metal raceways and metal clad cables. So that's probably what we would use. There probably would be threadless couplings or connectors. They're just simply more of compression type, and that would be fine. We could do that. And then also we have one other one that says, well, you could use listed devices such as bonding type lock nuts. That's probably the most common. We'll use a bonding lock nut. Or I can use a bushing. That would be a bonding bushing. Or I could use a bushing with bonding jumpers. Okay, so I have all these options. Now, typically, I see the bonding bushing with the bonding jumper. Just people don't know. Or if they got eccentric or concentrics or whatnot, they'll bring that equipment grounding conductor in on the primary side, and they'll loop it up through a bonding lug that's on the bonding bushing and keep on going. Remember, you're still going to have a bushing because you got to worry about abrasion. These are probably 4-gauge and large conductors, so you're still required to protect them as they come in through the raceway, so that requires the bushing. That's required over in Article 300. But in this case here, we're trying to deal with the bonding aspect of it. So that's what you need to do if you were using the general rule for the over 250 volts. Then you're going to use one of these options. And if it does have impaired connections like concentric or eccentric or impaired or oversized, then you're going to need a bonding jumper. If they're not going to have that, then you don't need the bonding jumper, but you have to have one of these other aspects. And so typically people use the bushing with the loop through, or they use a bonding bushing with the screw, and they'll bind that screw down into it, and they're perfectly okay. All right, but let's talk about the real world. Most of the time you're going to not run into any of that, and so we're going to use the exceptions here for this application in the 250.97 exception. So let's go back and look at the exception. So under the exception to all of that, it's the exception to go to 250.92. So I don't want to go there. So if I'm not dealing with concentric, eccentric, and knockouts, I'm punching my own holes, guys, then I don't have to go to 250.92b. I can use the exceptions right here. And those are a purely punched hole, or maybe if you did have concentric or eccentric, all of the knockouts came out and it was the right size you needed, then it's kind of no different than if you punched it out. I can use threadless couplings with connectors for cables with metal sheathing. So that's your normal couplings and connectors. I can use 2 lock nuts if it's rigid metal or intermediate metal. I got one on the outside, one on the inside. Not going to work for us here because we're using FMC. I can use fittings with shoulders that seat firmly against the box or cabinet with an electrical metallic tubing connector or flexible metal conduit connectors. Okay, and we got to have 1 lock nut on the inside. Then that's going to be okay. No problem. There's enough surface area connection. It's got a flat shoulder. Most all of those FMC connectors do. And of course, lastly, if it is a listed fitting for that type of wiring method, then it is okay as well to make that connection. So this is going to be all a really largely encompassing right here. Okay. All right. Okay. So that's how we're going to do it there. So bring it back to the PowerPoint. In reality, here, if I've got the equipment grounding conductor and I've got one of those accepted fittings and one of the, that are listed in 250.97 exception, because these conductors are over 250 to ground, then I can get away with just a simple fitting and a simple connector. Okay. Remember, I'm not worried about the lock nut limitation because I'm not going to 250.92b because I'm using the exception in 250.97. So then I'm done here. I come over here. Now, if you want to do a bonding lock nut, if you want to do where it goes through a bonding bushing, that's perfectly fine. You're okay. Remember, you still do have to bond this raceway. That's why you have to use the fitting and follow all those rules. But in reality, when it comes to the rule, under 250.97 exception, that fitting would be just fine and where everything's good. All right. Now over here, since this is really no different anywhere else, this is simply, since I have a supply side bonding jumper in here. Okay. So I'm not using this raceway as the supply side bonding jumper. I'm not using it as that. It's because it's not a fixed metal. If it was all EMT, I could get away with that, but I can here. So I have to bond it. So I bond it to this enclosure and I use the same listed fitting. Then it connects here. Then I don't need to have any type of looping on it. I don't need to have a bonding lock nut or whatnot. I can use a standard lock nut. Again, bushing on it because these conductors are probably, in our case, they were 350. They are larger than 4 gauge. So I would have a normal bushing on it to protect from abrasion. But there's no need to have any additional bonding over here. I see the looped conductors through these all the time. It's not required, but you can if you want to. Okay, that's perfectly up to you. It's not going to hurt anything. So let's look at some transformer example. This was provided by Bryce Bachman. Now, Bryce, you'll notice here, I don't see over here. I think, yes, he does have a lug here. So he's actually running his equipment grounding conductor through and then down. I think if you punched this hole, Bryce, you wouldn't have needed to do that. Over here, you do it again. Because this is probably, looking at the nature of it, this is probably flexible metallic conduit. A liquid tight flexible metal conduit in here. So again, you're not using this as the supply side bonding jumper. So it connects to a punched hole. So I don't see the need for you to do anything. A regular lock nut would work fine because again, all you're doing is bonding it. Okay. And you could come in and you make your connections here. Another thing to notice that 450.10 won't allow you to make any type of connections over top of the vent holes. So any of these terminations right here can't be through the vent holes. I've seen people actually do it because they can stick a bolt through it and make the connection in here. It cannot be located over any of the venting. Okay. This is where convection venting, air comes through, comes out the top, heat rises, pulls in air, and it kind of keeps this drive transformer cool. Okay. It does look like he has a system bonding jumper installed. I don't see any grounding electrode conductors, so I'm assuming that it's just incomplete at this time. And so the cover's off of it, so it's probably just not energized at this time. So they still got a little work to do. That's okay. You got a lug left to take care of it. Why can the grounding electrode conductor go here? Because he's using a wire type system bonding jumper, and that's code allows that under the exceptions to the rule, right? Okay. So that's good to go here. And let's see here. In this example here, this installation, they're coming in, and I don't know what method's being used here, but he's using a bonding lock nut. But again, if this is a punched hole, then you saw that these conductors, if they are over 250 to ground on the primary side, say 480, then it wouldn't require anything. If you weren't using those exceptions, okay, and you went to 250.92b, then this would be a viable option if you were doing that. But there's an exception to the rule now when it comes to over 250, okay, for that application. All right, over here, you've got, again, I don't see any bonding here because he's just simply using the lock nut. This tells me this is a punched hole, and I can't tell, but it's probably FMC that's coming down and feeding it. So now he's coming in with that supply side bonding jumper right here, connecting here, right? And I don't know what that is there. It's yellow, so maybe that's some kind of isolated ground. I have no idea. I don't know where the graphic came from. So this bear right here, I don't know what all this is about, but it looks like it goes down and up and over, and I'm not sure where it goes. But if that is the system bonding jumper, then it needs to come over here, not over here, over here. Okay. Anyway, just kind of wanted to give you some examples of some terminations, and you see how many things can be done to meet the rules. So I see a lot of transformers. Again, remember, primary side, 480, it's over 250. Follow the rules in 250.97. If the exception applies, using a listed fitting for that the FMC, then there's no real need for it. You are bonding it. You're not using that raceway as an equipment grounded conductor because you put that in the raceway. Okay, since it's used for flexible, then the requirements for FMC is going to require that you put an equipment grounded conductor in there. Okay, so it's already taken care of itself. All right, so that's in that side. So all you're really doing at this point is bonding. Okay, bonding, and it does have overcurrent protection on the line side of it. Okay, the primary protection of the transformer. So that's done there. And on the load side, again, we're dealing with the application where we're only bonding at that point. Okay, we're not using that FMC as an equipment grounded conductor. We're just bonding. If you want to loop it through and you think that that's going to help you in some way, go for it. If you want to put a bonding lock nut on it, have at it. It's totally up to you. But remember, we're dealing with circuits on the load side that, they're not service conductors. Okay, let's not get it confused with being just because they're on the secondary side of a transformer that they're service conductors. They are not. Okay, like we said, in our case, that primary side's only at 125%, the primary protection, so it's actually theoretically could protect the secondary as well. All right, so if that FMC gets energized, then it is bonded using a listed fitting to the enclosure, and all the bondings has been done, and you're okay. You want to use there is a requirement in 250.96, and that is, and we'll go look at it real quick. This is just a general rule, so it's good to make sure that you follow it. To 250.96, just so we can read it, is dealing with bonding other enclosures. So it just says that equipment, blah, 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 framing, members, and all of that are to serve as an equipment grounded conductor. All right. And of course, that FMC is not serving as an equipment grounded conductor. Okay. So keep that in mind. All right. So you don't get confused with that. So again, and we're not dealing with bonding over 250 volts for that requirement there. So really all we're doing with is dealing with the general bonding requirements. And these are bonding at the service, and this is bonding at the service equipment. So that's all the rules that we're encompassed in that. Okay. I don't know that there's anything else that we want to talk about in this video. I've done most of it in the video. So, I'll talk to you about one more thing. What about if we have? Let's come back to me. What if we have a transformer that's in a building that has metal water piping, or when we have metal framing of the building and it's exposed? Okay, so we got the metal water piping in the building, and it's in an area where that transformer is serving that area. Then we're going to look at 250.104, and we're going to learn a little bit of something about what to do. So this is a building where I might have the transformer. We've done all our other grounding and bonding, and we did everything. And now I've got metal water pipe, or I've got structural steel that is exposed. And the exposed structural steel or the metal water pipe is in an area that's being served by this specific transformer. Okay, the circuits that are in that area where this is at is being fed by that transformer. Okay, so we want to go look at 250.104 for some guidance on that. We don't want to leave without talking about that. All right, so 250.104, we're going to go down. So this is metal piping and exposed structural steel. So the metal piping is not necessarily exposed, but it's the exposed structural steel. So it's both of those. We're going to go down to item D, and that is dealing with separately derived systems. That's what we're talking about. It says metal water piping systems. So if there's metal water piping systems in the area where that's being served by that separately derived system or that transformer, and structural metal that interconnected to form the building frame shall be bonded. Okay. Now, that's the general rule. Now we're going to look at D1, D through D3. Now let's talk about the metal water piping. How do we do it? Okay, so we have a transformer. It's supplying a panel, and the panel is located in the area where this metal water piping is located. It says the grounded conductor of each separately derived system, okay, shall be bonded to the nearest available point on the metal water piping system in the area served by each separately derived system. Okay, so I have my transformer. It's serving a panel that's in this room, and the metal water piping system is in the area that's being served by this separately derived system. Okay, might be this side of the building or whatnot. It says the connection shall be made at the same point on the separately derived system where the grounding electrical conductor is connected. Okay, so it shall be made. So in our case, let's look at the graphic. So based on that rule, and let me go back here, excuse me, while I get us back. All right, it could be here, because that's where that's made, or it could be over here on the XO. Okay, these are an intimate connection. Okay, they're intimately connected. Okay, now I could have a bigger bus with everything going to the XO and all these other, all could be one, but that's what we're dealing with that one. Okay, oops, sorry about that. All right, so we've established that. So it can be made there, but literally it has to connect the grounded conductor to the metal water piping system, and it is allowing me that it shall be made at the same point where the grounding electrode conductor is connected, and we showed where that was in our graphic. And then it says each bonding jumper shall be sized in accordance with table 250.102C1 based on the largest ungrounded conductor of the separately derived system. All right, and we're not going to get into the exceptions. You can read those. We're going to talk about the general rule. We're going to always talk about the general rule here, and not going to get into those. Okay, and basically we can kind of know what we did before. Since we were dealing with this system here, and let's say over here was the metal water pipe. Since these are based on these conductors were 350, then we go to 250.102C1, and we'll know that it's actually the same size as these. So it would be a 2 gauge. So we'd run a 2 gauge, and that's what we'd run over to the water pipe ground. And that's how we do it. Again, it's based on these conductors utilizing 250.102C. Okay? All right. So now let's go back and look at the code a little more. Now we're going to move on to the structural steel. Now here's a big thing. If exposed, and it's exposed structural metal that is interconnected to form the building frame, and it's all kind of going together. We're not talking about isolated pieces of metal framing. We're talking about exposed metal that are interconnected, that is actually forming the building frame. Okay, not if it was wood framed and we had some beams that were metal. That's not integrated into the form of the building frame. Okay, that's just kind of a little separate. Okay, exists in the area served by the separately derived system. It shall be bonded to the grounded conductor of each separately derived system. Okay, this connection shall be made at the same point on the separately derived system where the grounding electric conductor is connected, and we already discussed that. It's no different than where it was for the water pipe ground. It's also sized the exact same way. So obviously this would be a 2 gauge for the structural metal as well. Okay, all right. And again, if you had multiple separately derived systems, then each one of them would have to go make a connection over to that structural metal. Okay. Now there's a third option. The third option says, well, what if I have a common grounding electrical conductor? And that's a conductor that runs from, say, first floor all the way up a chase to the 10th floor. And that's called a common grounding electrical conductor. And if that's the case, then I can make the connection over to it. So if a common grounding electrical conductor is installed for multiple separately derived systems, it's just a convenient way to do it. And they are permitted you to do it that way under 250.30A6. And if that's the case, the exposed structural metal that is interconnected to form the building frame or interior metal water piping, if exists in the area served by that separately derived system, kind of regurgitating what we already know, it says the metal piping and the structural metal members shall be bonded to the common grounding electrode conductor in the area served by the separately derived system. Okay? All right. All right, so now again, we have some exceptions. I really wasn't going to get into these, but I'll talk about one of them, and we'll just talk about it and move on. You want to read it yourself. They're not complicated. You just have to read them. So the general rule here was to take it to the water pipe, right? and it says that you would use 250-102C1 to do it. So this is the rule. So there's exceptions. So the exception says a separate bonding jumper to the metal water piping shall not be required if the metal water piping system is used as a grounding electrode for the separately derived system and the water piping system is in the area served. So if it's already having this, let's go back and I'll show you. If you already had the requirement for this grounding electroconductor to go to the water pipe ground, then it's pointless to take another one out to the water pipe ground to the metal water piping of the system in the building. It would be pointless, right? So that's the exception. It says, all right, you've already done it once. You don't have to do it again. We don't need to do it twice. Okay, so that's what that rule means. Okay, and this one here, it says, again, a separate water pipe bonding jumper shall not be required if the metal frame of a building or structure is used as the grounding electrode for the separately derived system and is bonded to the metal water pipe in the area served by the separately derived system. Okay, so basically what that's telling me is, look, I don't need to run where I have a separate water pipe bonding jumper. It's not going to be required to do that if that metal frame of a building or that structure is actually being used as a grounding electrode for that separately derived system. And of course, that building and structural metal framing is actually bonded to the water pipe system in that area. And that's where you tie all of the electrodes together in a system. So obviously if both of these are there, the requirements in 250.50 requires that you tie them all together. So it would be kind of pointless to, run another one. What's the point? What are we going to get from that? God, I'm looking green. I should have checked the tint before I did this video. All right, this is my blooper. I look like I'm a Martian. Okay, so we'll go back here, and I might as well while I'm here. The other exception here, these for the structural metal, it says a separate bonding jumper to the building structural metal shall not be required if the metal frame of the building or structure is used as a grounding electrode for the separately derived system. Okay, kind of the same concept, and it's no different down here. It's all the same. Okay. So that covers all of that, and you know what? That's all I'm going to cover for the basics. So we size an equipment grounding conductor, we size the supply side bonding jumper, we size the system bonding jumper, we talked about the bonding, whether it was over 250 volts for the primary side. If not, we can just use all listed products and bond it. If we're not encompassing concentric or eccentric knockouts, things like that, then we don't use bonding jumpers. We are allowed under the ones that are over 250 volts to utilize the exception that doesn't send us to 250.92. But in that exception, we can use listed fittings. We could use just regular FMC. In our case, the FMC connector is got a flat surface and it's designed for use and it's listed, so that wouldn't be a problem. If you want to do all the other looping and you want to do the set screws, the bonding type lock rings or whatever you want to do, go for it. It's not going to hurt anything. Some jurisdictions require it. Some just don't understand, and that's fine. If you want to do that, perfectly fine. It won't hurt anything. And some people will say the more the better. So if that's what you want to do, go for it. Remember, we're not using that FMC as an equipment grounding conductor. We're only bonding it in a sense in case it gets energized. So it's more a safety concern, okay? And the proper fitting connected onto the metal enclosure, making sure that's a good connection using the fitting and a lock nut that actually digs into it, a bonding type lock ring that's actually designed with the teeth that bite. We've used it all the time for feeders. We just couldn't use that standard type of lock nut when we're dealing with service conductors on the actual service, or in this case, we couldn't use it also for over 250 volts if we and under that allowance, if we had bonding jumpers that required. So we couldn't use it. So we have some of the other allowances that we can use there. So in our case, for the primary side, it's over 250 volts. I'm just going to use a listed fitting that's going to give me the flat surface. I'm going to follow one of the ones, threadless connector and all that. Then I'm going to be fine. I don't need to do anything extra. It's going to work fine. If you want to do it, okay, go for it. All right, guys, that's all I'm going to do in this video. It's about an hour long. The next video in this series, we're going to talk about how to size the grounded conductor. We're going to talk about how to balance a Y and a delta transformer. That's going to be cool because you got to do all that stuff first. So we're kind of work this backwards. We learned back in part 1 how to determine the primary current and secondary current of a transformer. Part 2, we learned how to do the overcurrent protection of the transformer, sizing conductors in part 3 and 4. Right now, we got into grounding and bonding, the basics. In the next one, we're going to kind of go whereas what do you do to actually size that transformer? So we have to balance the loads in the panel. We have to balance the transformer windings so we don't burn them up. We have to size all those. And then, of course, we have to have a grounded conductor that's no less than what's required in 258.102C1, the table, but we also have to size it for the unbalanced load. And I'm going to show you how to size that as well, but it can't be any smaller than what's required in 258.102C1. But you need to learn how to do all the calculations for that, and I saved that for last. So hopefully you got something out of it. God bless. Until next time, stay safe.